So in mathematics, sometimes we have different measurements for the same thing. And sometimes those measurements are in the same family. Like you could get a drink that's 500 mils, and the next one's labeled as half a liter. Those are the same thing, just with different measurements in the same family. And sometimes you get measurements that are completely different families. For example, if I ask how tall are you? How tall are you?
6'1".
6'1", okay. How tall are you?
5'4".
5'4". Is there anybody who knows how tall they are not in feet and inches?
175.
175. So depending on, what country you're from, your measurements of your height will be different, right? Some will say centimeters, some will say feet and inches. And it's not that 175 is a monster in height compared to 5 foot something, right? It's not like, wow, he's like 25 times taller than him because he's 175, the other guy's only 5. But they're measurements that are different. And what we're going to learn is that, as with many things, there's a different measurement for angles. We have learned up till now only to deal in degrees. Go all the way around, 360 degrees. In a triangle, often you have a 90 degrees. So we have experienced degrees along the way. But now we are going to get introduced to a new measurement, which is called a radian. And the way that a radian works, 1 radian is when, right, from here to here, would you agree that that's your radius? And if you travel an arc length exactly the length as your radius, that's what makes a radian. Now, to give you a visual of approximately how big is a radian compared to degrees, is I've got a little cardboard triangle here where supposedly, it's getting a little bent, supposedly all the sides are the same. What kind of triangle? Do you know the name of this triangle? It's got a special name when they're all the same. Starts with an E. Rhymes with equilateral. Equilateral. Your equilateral triangle has all 3 sides the same. It also has all 3 angles the same. In this triangle, all 3 angles are the same. All 3 angles would be 60 degrees. Now, if I take this equilateral triangle and put it on the edge of the circle, I could bend, push it down a little bit so that it matches perfectly with the green that I've drawn. And at this moment, we could say, well, if my equilateral triangle was all 60 degrees, and I squished it a little bit so that this side bent perfectly along the edge of the circle, we could say that 1 radian is a little less than 60 degrees. Now, in a pre-calculus class, that doesn't go over very well, because in pre-calculus, we like to be exact. So someone coming up with a definition, oh, it's a little less than 60 degrees, might make you feel like I want to come up with a better way of measuring this. So the next thing that we can look at is how can we compare this measurement to degrees to get something exact. And the key is thinking about arc lengths like we were thinking about before. So if this arc length is r, the question is, what would the whole circumference be? Right? We know that the whole circumference is 2 pi r. And maybe not, you've never thought about this formula as actually, this is a number, right? 2 pi is 6.28. and r is your radius. So if my circumference is 6.28 r, check this out. I have measured with 1 radian, 1 radius. I could measure another radius, another radius, another radius, another radius, another radius, and then there's a little bit left over. If we count how many radiuses there would be, there's 6 and a little bit when we draw it out, but if I take 2 times 3.14, I get 6.28. That's an approximation. Of course, pi continues forever. So your circumference formula actually tells you how many radiuses there are around the circle. And every time you have 1 radius around the circle, you get 1 radian. So if there are 2 pi radiuses in a circumference, this means that there are 2 pi radians in a circle. Does that make sense? If I can measure 6.28 radiuses around the edge of the circle, and every time I have one of those radiuses around the circle, that would give me 1 radian, then I can say that there are 2 pi radians in the whole circle. Which leads us to the following conclusion. I can make a chart. In a whole circle, there are 2 pi radians. That means, in a whole circle, there are 360 degrees. And this is actually highlighted on, so this is highlighted on page 489. That 360 degrees is 2 pi radians, because once around the whole circle in degrees is 360 degrees. Once around the whole circle in radians would be 2 pi. Can you see that you could divide both of those by 2 and write the following? Halfway around the circle, well, in degrees, halfway around would be 180 degrees. And in radians, halfway around would be 2 pi. Just pi. And if you wanted to take this even further, okay? If I wanted to get 1 radian by itself, what would I have to divide this side by? I'd have to divide by pi. So if I divide this side by pi, in order to keep it equal, I'd have to divide that side by pi. And we get 1 radian is exactly 180 degrees divided by 3.14. Our definition before was a little less than 60. If we type 180 divided by pi into our calculator, a little bit less than 60, it's approximately 57.3 degrees. And similarly, if you wanted to get 1 degree by itself, and you see that you could just take this one and divide it by 180, then you would get 1 degree by itself, and then you'd have a conversion for converting from degrees to radians. Now, these 2 in the blue boxes are very helpful for converting back and forth, because we need a conversion rate in order to change from one thing to the other. Just like if you wanted to change from inches to centimeters, you'd have to multiply by 2.54. So these are going to be the things that we're going to need to use to multiply by in order to change from radians to degrees. Also, off on the side, right beside this, I would like you to rewrite out your formula that we learned yesterday. Our arc length in degrees that we found out yesterday was just a proportion out of 360 of the circumference. We can now write out an arc length formula in radians. It will also be a proportion, but instead of out of 360, we would do out of 2 pi. And this one is on your formula sheets, but the mathematicians just could not help themselves in simplifying this. Again, I actually like leaving it like this as a proportion of the circumference. But it was just too tempting for mathematicians not to cancel out that 2 pi. So we have a very simplistic and beautiful arc length formula, but this formula only works in radians. And that formula is on your formula sheet. So when we get to example 1, we are just going to practice changing from radians to degrees and degrees to radians. So number 1a, we have 170 degrees. And off to the side, I'm going to write out that 1 radian is 180 over pi, and 1 degree is pi over 180 radians. And you have to think about, if I want to change 170 degrees into radians, which one am I going to multiply by? Am I going to multiply by 180 over pi or pi over 180? And this could be confusing because you can see they're very similar. Okay? One of the things that I sometimes do is I sometimes say, well, of these two formulas, which one would it be easiest to multiply to get 170 degrees? That would be the second formula. So if I started with the second formula here, and I multiplied this side by 170, do you see that you would get 170 degrees on this side? But then I would have to multiply this by 170 as well. So sometimes people like to do it this way, okay, where they are multiplying, they look at the formula and see which one could they multiply to get 170 degrees easiest. Sometimes people like to think of it this way. If I start with 170 degrees, the reason I can multiply by pi over 180 is because pi radians is the same as 180 degrees. What you are essentially doing then is multiplying by 1. When we multiply something by 1, we don't change what it's equal to, but sometimes we change what it looks like. Like, for example, with fractions, sometimes you multiply by 3 over 3 to get a common denominator. You're not changing the value of the fraction, but you're changing what the fraction looks like. So another way that sometimes is helpful for understanding is if I have degrees up here, I would need degrees down here so that unit cancels out. And then the only unit I would be left with is radians. And then my final answer would be in radians. Here, if you multiply by the other one, you have degrees on the top and radians on the bottom. So if you would want to get rid of the radians, you would multiply by 180 over pi. Two different ways of calculating this. Now, if you leave your answer as 170 pi over 180, perfectly fine. In grade 12 pre-calculus, you do not need to write your fractions in simplest form. You can if you want to, but you could leave it as 170 pi over 180. So it says, give the exact measurement. This would be considered exact. And when we go to our calculator and we type in 17 pi divided by 18, then we get an approximation to the nearest hundredth would be 2.97. Part B. Given theta is negative 12 pi over 11 radians, sketch the angle in standard position and determine its measure to the nearest tenth of a degree. I'm going to say, for this one right now, where you are at, you would probably like to do the second part first. We're going to first convert this to degrees because your brain is able to think in degrees, right? Better than it can think in radians, right? If I asked you where you're standing, turn 55 degrees to the right, you probably could do it fairly accurately, or at least have an idea. If I told you to rotate 7 pi over 6 to the right, radians, you'd be like, I have no clue at this moment. We're going to get there. But right now, your radian thinking isn't very good. So we're going to start by changing this to degrees. We have negative 12 pi over 11. And if we want to change this from radians to degrees, we would multiply. Because we imagine that there's a unit here that says radians, and that imagine that there's pi has a unit of radians, and that these would cancel out, leaving you with just the unit of degrees. We also notice that these pi's simplify. That's nice. So if I get 12 times 180 divided by 11, I get 196, approximately 196.4 degrees with a negative sign out in front. And now, if you were asked to draw that in standard position, remember that standard position always starts from the positive x-axis. Negative would go past 180. But we're also going to learn how you would think about this using radians. So I think measuring negative 196, you'd probably be pretty good at that. Measuring in radians, again, you would be starting here. Halfway around is pi radians. 180 degrees is pi radians. 360 degrees is 2 pi radians. So if halfway around is pi, this, going in the negative direction, would be negative pi, and I need to go negative 12 pi over 11. I want to go negative 12 pi over 11. Can you see that that is equal to negative 1 and 1/11ths? changing it to a mixed fraction. So here, this would be negative 1 pi, and we need to go 1/11 more. So I imagine this whole length split into 11 equal sections. And that's how I could think about this in radians using my knowledge of fractions. I would see that this fraction is negative 1 and 1/11. So negative 1 pi would be halfway around the circle. 1/11 more is imagining this section split into 11 equal parts, and I just went 1/11 more. So we're going to be thinking a lot in fractions, fractions of half of a circle, fractions of a whole circle, when we think in radians. Okay. There's a shortcut. There's a shortcut that often happens when changing radians to degrees. If there is a pi, and there's not always a pi, so the shortcut doesn't always work, but if there's a pi, you can just change the pi to 180. So if we look at the example we just did, we had negative 12 pi over 11. Why are you allowed to do this shortcut? If you look at the math, when you multiply by 180 pi, can you see that the pi's would cancel out every single time? And if the pi's cancel out every single time, and what gets replaced where the pi was? 180. So we get that as a shortcut that we can do. We can replace the pi with 180 degrees. Okay, so part C, 7.5 radians, we want to change it to degrees. So we would multiply by 180 over pi. Can't use the shortcut here. So 7.5 times 180. $429.7 degrees. In mathematics, if you're talking about an angle in degrees, you must have the degree sign. So then you ask, what is the unit for radians? There is none. So when you leave your degree sign off in grade 11 math and you say the answer is 30, if you wanted to say 30 degrees, when you say 30 without the degree sign, technically that means 30 radians. Whenever you leave a unit off in an angle, you are now talking radians. It'd actually be helpful. I know some teachers create their own unit when they're dealing with radians. I know one teacher that makes a degree sign and puts a little R inside of it. That means radians. But there is no unit for radians. So if you're lazy and forget your units, you're fine when you're in radians, but you will always lose marks if your answer was supposed to be in degrees. Because do you know how much a difference is? Okay, think of it this way, 30 degrees, right? You know what that is in degrees. I can jump, and I can land 30 degrees pretty good. 30 radians all the way around once is 2 pi, which is 6.28 radians. 30 radians is almost spinning 5 full times around in a circle. I cannot jump and do that. Probably can't even do one. There's your challenge. When you go home, find a place that's safe to fall down, jump and see how much you can spin in the air before you land. There you go. There's your active mathematical challenge for the day. Okay, questions for practice on this one are 4, 5,